In the last video, we looked at some basic work with vectors in both 2 and 3D. In this video, we're going to look at the vector equation of a line. To begin with, we're going to consider a basic example from mechanics and look at the movement of 3 different ships. So in 2D, we're going to have the standard Cartesian coordinate axis, where we've got an XY plane. We looked at the origin in the last video and I and J notation. I now corresponds to the x-axis, J corresponds to the y-axis. What we're going to do is look at the position of 3 different ships at any given time t. T might be hours, it might be minutes. So let's start off with one ship. I'm not going to do these too accurately, but all we'll do is plot them. What we can say is the position vector. Now a position vector is relative to the origin. The position vector of A, ship A, at any given time is given as where it starts. And in column form, I'm going to say that this is 2, 1. So what we've done relative to the origin, we've gone across 2 and up 1. Plus now some multiple, and my scalar parameter is t. T is time. And we multiply this by a velocity vector. So let's say that this is 3, 2. So what this is saying is this ship will now start here at 2, 1. That is the position vector. So if I went for 1 hour, I would simply add 3 and 2. It's going across 3 every hour, and it's going up 2. So what we're going to have a path, and it's going to look something like so. So we're going to go across now 3 and up 2. So let's say it looks something give or take like so. So after an hour it will be at 5, 3. After 2 hours we will be at 8, 5, and so on and so forth. So this now is a basic vector equation of a line in 2D. Okay, let's pick another ship. Let's just put it out here. And we'll put that point just here. And we'll say that this is ship B. Now RB, the position of B at any given time t, is where it starts. So let's say 4, 5. Let's say it starts here. Plus now some multiple, and remember, this is the velocity vector. Velocity is telling me how far it's going across for how far it's going up. So let's say that this is 6. Let's do this as 6, 4. Now, if we look at these 2 velocity vectors, or more in general, the 2 direction vectors when we come on to the equation of a line, what we'll have now is one multiple of the other. We can see that this velocity vector is twice the size of this one. That means that these are parallel lines. These are never going to crash. These 2 ships are running now essentially alongside each other. This one is just covering twice the ground. So this now would be the vector equation of a line, where we start plus some multiple of this velocity vector. Okay, let's put another ship out here. Let's just choose one. Let's go for, we'll put it just here, okay? And we'll say that this now is the position of C at any given time t. So let's say that starts at 5, and let's go for 5 minus 2, and we will give it a velocity vector now of, and we'll go for minus 1, 6. So this is going left 1 and up 6 every hour. Now, there may be a point here where these 2 lines intersect, and what we're going to do is solve for that. So what we'll see is the following. Now, because this ship is moving as such, we might go behind it. But what we're looking for now is the value of t where these would collide if they did. As we go on with our work in vectors, we will see now that these lines, essentially, the ship is going to be moving away, but it'll give us some idea now that these 2 lines are going to intersect, and we would simply solve for the parameter t. So I appreciate with the ship moving along the line, it's potentially the case that they're not going to intersect, but all we're going to do now is look at these 2 lines intersecting. So if you want, you could see this as 2 of these crashing, or you could see this as where have the trails met. So let's go ahead and solve this. What we want are the I and J components of this particular position vector to be equal. So 2 plus 3t for this ship right here. This is telling me where it's going to be. So 2 plus 3t must now be equal to 5 minus t. 1 plus 2t, so 1 plus 2t will be equal to minus 2 plus 6t. So let's go ahead and solve now for equation 1 in terms of t. So what's that going to give me? 4t is equal to 3. So we can say that t is equal to 3/4. Now, if I solve this one, are we going to get a point of intersection? Yeah, 4t is equal to 3, t is equal to 3/4. So what this is telling me now is after 3/4 of an hour or 3/4 of a minute, these will meet. So if I think about this now, what I'm going to get for the I component here is going to be now 2 plus 9/4. So we're going to have 2 and 9/4. That's where these are going to meet. If we now look at the J component, what we're going to have now is subbing this in. We can put it into either one of these two lines. We've got now 1 plus 6/4. So 1 plus 6/4, which is 1 plus 3/2, which is going to be 2.5. So that's what it's telling me. It's telling me that they are going to meet at this point. I appreciate in this example, if a ship's gone past, then they're not going to actually crash, but their paths will cross in terms of where they've been. What we're going to go on to do is look at how this works with now the equation of lines in 3D or free space. So that's a basic example now of vector equations of lines and points of intersection. So what we're going to do now is look beyond these couple of scenarios and move on to 3D. So with 3D vectors, we either have now parallel lines where the direction vectors are multiples of one another. We have lines that intersect and we can solve for some value of t or lambda or mu, our scalar parameter, or we have the third scenario where we have skew lines. Later on we'll look at skew lines, but if you'd like to think about that as the paths of two different planes, now essentially in a 3D plane, you would see two aeroplanes, you would see that there are going to be now paths where they neither intersect nor are they parallel, and we call those skew lines. So let's start off with some basics and work in 3D. Now this can be given in 2 or 3D. What I'm going to have is now, and just sketching this up, we will have the coordinate axis. So let's just start off with, we could of course put this now in with 3D coordinate axis. So if you like, here are the 3D coordinate axis. So let's say we've got now X, Y and Z. It's often easier to see this in 2D, but if you wanted, you could say now that we've got the X, the Y and the Z. These are now mutually perpendicular axes. So let's start off, and I'll do this to begin with in 2D. What we're going to have is a position vector. We'll have a position vector, and that's going to be, let's say that was, let's put it just here. Let's say that is going to be A. We're also going to have a position vector now R. So let's look at these vectors relative to the origin. What we can say now is that this is going to be A and this is going to be R. So let's just draw those up. So this now is going to be, and we'll just show this with a vector, this is going to be A. So in a book we would see this now as bolded. If we're writing it, we would simply write now lowercase a with a line underneath. And this is going to be R. If we consider now the vector AR, that's simply now going to be some direction vector. So if we look at that now, and I'll put this on, that's going to be a direction vector. And in the last video we looked at that. So if we liked, we could call that direction vector. Let's just call that now, let's say that's going to be D. So what we've got then is the following. We can say now that this is going to be D. So AR is equal to D. We can see that A, now, this position vector, we can see that A is the position vector OA. We can see now that R is the position vector now OR. What we're going to do is look now at the vector equation of a line. Now, all we need to write is the following. We say R is equal to now A. So what we've got here is A, and I'll just write it here, plus some multiple, and I'm going to use a scalar parameter now, and I'm going to either use, we could either use lambda, or we could use mu, or we could use t. I'm going to use lambda, and we can say now that this is going to be some multiple of the direction vector. So more informally, what we do is go from the origin to a point that we know on this line, and then all we're looking to do is say now that this vector R is going to be some multiple of the direction vector. So let's look at that in action and actually do one of these. So say we've got now that A, let's put A on here, we've got A, let's say, and just looking at this, let's say that it's going to be minus 1, 2, 2. Let's say that we've got now R is going to be, let's say that's going to be, we'll go for, in fact, let's make this one minus 2. Let's go for minus 2. Let's say this is minus 1, and let's say that this is 4, and let's say this is 6. This now is the vector equation of a line. What it actually is R is equal to OA, so we're jumping on to this line, plus some multiple now of AR. And remember, in the last video, we saw now that AR was equal to R minus A. So what we're going to do first is look at AR. The direction vector AR is simply going to be minus 1 minus minus 2, which is going to be 1. Then we're going to have 4 minus 2, which is going to be 2. And we're going to have 6 minus 2, which is 4. So what I can say then is R will be equal to now the position vector of A. Now I'm choosing A. I could have chosen R. So what I'm going to have then is the position vector, and we're going to have now minus 2, 2, 2, plus some multiple now of the direction vector 1, 2, 4. Now, what does this mean? Well, this means now that that is the vector here. So I've gone up and I've jumped. Now, in this particular case, if we look now, if lambda was equal to 0, we would end up just here. So that's all we're doing. We're simply saying now, if lambda was 0, we would end up here. If lambda was 1, we would end up at this point right here, R. Now just consider, that makes sense. If I'm just adding one lot, I'm getting to R. Now, if I altered my scalar parameter, what we would end up having is the following scenario. We would end up having, and I'll put these on like so, we will have, and let's do a different colour. Let's do that one. Now, if we had R is equal to 0, we would be just here. If lambda was equal to 0, we'd be here. If lambda was equal to 1, we would be here. If lambda was equal to 2, we would be here. All we're doing is finding now a multiple of this direction vector and moving now up and down the line. So R is given now. So this might be, and we'll put some of these on. Let's do these. Let's put that one just there. Let's put that one just there. And let's put that one just there. So what we've got then are the values of lambda. So let's say now here, and we'll get a different colour. Let's go with that one. We can say at this point now, the value of the parameter is going to be 0. Here, the value of the parameter is going to be minus 1. The value of the parameter here is going to be 1. The value of the parameter here will be 2. So now, if we subbed in minus 1 here, what we would get now, and let's just say that, let's call this point here, this one, let's call this, let's say this is P. What we can say then is RP will be now minus 2, 2, 2, and then what we're going to have now is plus minus 1, lots of 1, 2, and 4. So we're going to end up now with RP, so RP will be equal to minus 3, and then we'll have now 2 minus 2, which is going to end up giving me now 0, and then we're going to have 2 minus 4, which is minus 2. So whilst inaccurate, we could say that's minus 3, 0, minus 2. So minus 3, 0, minus 2. Informally, what we're looking to do is get now a position vector to jump on this line. This line, the direction vector, is simply AR. Then we're looking for scalar multiples. I'm using lambda. You might see mu, or you might see t. All these are now our multiples. So in this particular case, we can say RP is going to give me now this position vector. It's on this line. It's jumping around, and we can see as we increase now lambda, we're going to move in this direction. So this was where lambda is equal to 1. Let's just put that there. This is where lambda is 0, and so on and so forth. So essentially, if we scale that down, what we're going to have is something that looks like so. So these are going to be now A and R. This now is our direction vector. So that's the direction vector between the two. So coming from the origin, what we've got here, now let's put that on. We've got now A, we're jumping onto our line, we want to get onto the line, we're looking for a point we can locate on the line. That corresponds to this value right here, or if we like to write it in this form, we have it like so. and then what we're looking for is some multiple of this direction vector AR. So if that was equal now, let's put on, and we'll put lots of these on. Let's say now that that multiple was equal to 1/2, we would end up there. If it's equal to 2, we would end up there. If it's equal to 3, we would end up there. If it was equal to -1, we'd end up there. And these are all now position vectors on this line. And these would just be given relative to their name. So let's say that this is Q. This would be RQ. If we said that this point now was, let's say, S, this would be RS. So that is a basic equation now, a vector equation of the line. So in this one right here, we could write this as R is equal to minus 2I, and this is using IJK notation, plus 2J plus 2K, and then we're going to get now plus some multiple, and that is my scalar parameter of I plus 2J plus K. So in column form, and then now in the vector IJK notation. So formally, this now is the vector equation of the line. More informally, now if you've got 2 points, and let's just say they're A and B, you go up to A, and then you simply add some multiple now of the direction vector AB. So it's going to be R is equal to A plus some multiple now of this direction vector AB. Now, we could, of course, say that we can jump onto the line at B. I've just chosen here A. I could have jumped onto the line here at R. I could have jumped onto the line at B. It's entirely up to you. Now, you will be guided, but essentially these are just different forms that you can put the equation in. We're now going to look at 3 different scenarios with these vector lines. Remember, these vector lines are infinitely long. So, for example, if I wanted to draw, in the ship scenario, we looked at a starting point. What we've got here is something that's going to look like so. So these could be 2 vector lines. Now, what I'm going to do is draw these up. Now, initially, we've seen what the parallel vectors look like. What I'm going to do here is do some other scenarios. So these are now our 3 mutually perpendicular axes. And often it's hard to get your head around this. Essentially what we've got now is the x-axis, we've got the y-axis, and then different orientations in different books will show you different things, but that is now the z-axis. So if you like to think about this now as the corner of your room, this is the back wall, and if you wanted to get a wire from the wall, you could bring it up. So let's just do that. Let's grab up a wire. So say this was in the corner of your room. That's now the wall up, this is the wall across, and this is the wall across. So if I get this bit of wire, I could just walk along the back wall. I could just walk along the side wall. I could just go up the wall. Alternatively, I could come out a bit, across a bit, and up a bit. And it's hard to see this in 3D, but essentially what this is now is a directed line segment that has gone across one way, across the other way, and then up. So imagine that I was just standing below this, holding this piece up. Now, what we've got are different scenarios. So this might be a vector like so, okay? And it might be there. Now, we can have parallel vectors, and we've seen those. So what we would have is the first scenario, and that's now parallel vectors. And they would look something like that. Now, if parallel vectors are, or if 2 vector equations of a line are parallel, essentially what we're going to have is one multiple of the other when it comes to their direction vectors. So let's look at an example. Let's say R1. What we could say is R1, and this might be, let's say that this is going to be line 1, and let's say this is going to be line 2. Let's say now, and ignore where these are just, let's just give them some arbitrary values. Let's say that this is 1, 0, 4. So this is where I've jumped onto the line, plus some multiple now of, and we're going to have a direction vector. Let's just say that's 1, let's say 1, 2, 3. Let's say that this is line 2 and its position R2 can be given now, and we'll just start it somewhere else on that line, and we could say, let's just say this is -1, 3 and -2. Now if this is some multiple, and I'll use mu, generally lambda and mu are used, or S and T, often S and T, lambda or mu. Let's say that this now is going to be 4, 8, 12. What we could see from this now is that this is now parallel. We could take a factor of 4 out of this and write this now as 4, and that would give me 1, 2, 3. as you can see, this has got the same direction vector as this one. It's moving in now the same direction. That means that these two are going to be parallel. They will never intersect. They will just continue in 3D or free space now following these vectors. Often you'll see now that this is going to be factored into our scalar parameter. It's just one multiple. So what I could do here is actually write R2 is going to be equal now to minus 1, 3, minus 2, plus some multiple, and let's just call that S, and I could write that now as 1, 2, 3. So in your work you have the option now of scaling these down and simply writing a new parameter. So they now are parallel lines. If we've got parallel lines, the direction vectors are simply one multiple of the other. These are moving with the same I components, the same J components, and the same K components in terms of their direction. Their magnitude, the size of them might be different, but the direction is the same. Now, the second scenario is that we have two lines that intersect. So let's now look at that. And what I'll do, I'll put these on. Let's see if we can put them on like so. Hopefully this won't be too much of an eyesore. But what we might have now, in fact, let's change the colour. What we might have is a line here, and we might have one just here. Now, these might intersect. So let's just give these two equations of lines. Let's say that this is going to be line 3, and let's say this is going to be line 4. So what we're doing now is looking at the intersection of two lines. The first scenario I gave when we looked at the ships, it was slightly different because essentially the ship was moving. In terms of the vectors, we will see that these are really just two static lines in free space or three-dimensional space. So let's give these now two equations. Let's say, let's go for, let's say now that let's say R4, let's start with R3. Let's say R3 is going to be 2, and then we can go minus 3, minus 7, plus some multiple now of the direction vector. So this is moving in the direction of 1, 1, 1. Let's say R4 is going to be some now position vector on that line. So let's say that, let's go for, let's say 4, let's say minus 6 and minus 14. And then we're going to have plus some multiple, which I'm going to say is mu. Mu and lambda are just simply now the scalar parameters. And we could say, let's go for, on this one, we will have, let's have 0, 0.59. So let's write that in here. Let's go 0.59. I'm just hoping these will intersect. So what we're going to do then is define. What we want to do, if these are going to intersect, we need to consider now setting up simultaneous equations to solve for some value of lambda that holds true and some value of mu that holds true for each equation. So what we would say, for their I components to meet, so essentially for the x coordinate to be the same, 2 plus lambda must be equal now to 4, okay? 4 plus 0 mu, so it's just going to be 0. Now, if these are going to meet, what we're going to have is minus 3 plus lambda is going to be equal to minus 6 plus 5 mu. That would be where their j components meet. Minus 7 plus lambda is equal to minus 14 plus now 9 mu. So what we've got is equation 1, 2 and 3. What you need to do in an exam is show now that in this particular case, these hold true for all three equations. It might become obvious that that is the way. But if we look at this now, what we've got, let's take equation 1. From this now, we can see 2 plus lambda must be equal to 4 if these are going to intersect. Therefore, we assume they intersect and we say that lambda is equal to 2. Now, if I sub this into, so let's just say that's equation 1. If I sub this into equation 2, what we've got then is minus 3 plus 2. So minus 3 plus 2 is equal to minus 6 plus 5 mu. So let's go ahead. What's that going to give me? That's going to give me minus, what are we going to get? That's going to be minus 1 plus 6, which is going to be 5. Oh, that works out quite nice. 5 is equal to 5 mu. Therefore, mu is equal to 1. So that's saying now for this particular scenario, if I'm using 1 or 2, at the moment we've got a value of lambda of 1, we've got a value of mu for 2. We need to check that in equation 3. So let's sub that in equation 3 and see if it works. So what we can say then, equation 3 is as follows. So what we've got then, just here, we've got the value, and we've written down what have we got? We've got minus 7. So let's just check if we're right. So we've got minus 7 plus 2, and we want that now to be on here minus 14 plus 9 lots of 1. And you'll probably sub that into show. Now that's minus 5, and that is equal to minus 5. Therefore, it works for all three equations. So all we need to do to find the point of intersection is simply sub in either lambda is equal to 2 or mu is equal to 1 in either of these. So if lambda is equal to 2, what I can say now is the position, and we might want to say that they intersect, let's say they intersect at the point P, we can say that RP will be equal now to 2 minus 3 and minus 7 plus now, and I'm going to have 2 lots of 1, 1, 1. So what's that going to give me? RP will be equal to, that's going to give me 4, that's going to give me minus 1, and that's going to give me minus 5. So we can say now that these meet with 4i minus j minus 5k, and that now is in vector form. That's a position vector where they meet. Now if we'd done this here and subbed in that mu was equal to 1, what we'd see quite clearly is that we're going to have now 4, then we're going to have now minus 6 plus 5, which is going to be minus 1, and then we can see that we got minus 14 plus 9 as mu is equal to 1, which is going to give us the value of minus 5. So we can see that those two lines intersect. They intersect in free space. So for example, if you're in the garden and when you're a kid and you have 2 canes and you're playing in a fight with your brother or sister and you put the canes up in the air and hit each other, then they are going to meet at some point in 3-dimensional space. Or if you like, if you've watched, Star Wars with the lightsabers, that's what's happening here. So parallel, we've got intersection points, and then finally our last scenario is that we have skew lines. Now the best way to think about skew lines is just to think about 2 jet planes in 3D space. So what we'd have now, and we'll try and get these on, let's say, in fact we'll change that one to a different colour, make it slightly easier to see. We might have a jet plane going here. Now this one, it looks like this is going to intersect it, but consider now that that is flying under. There might be 100 metres between these, there might be loads. This now is on the path here, and this one is flying below. So these are now skew lines. When we've got skew lines, we will see now that we can't solve for lambda and mu to give us the same value. So let's just choose some. Let's say we've got now, let's say we've got RA. So we're given line A, and we can say line A is going to be 7, let's say 7 minus 4 and 6, plus some multiple now, and let's go for minus, let's say minus 2, 3 and minus 1. Let's say RB, okay, we will have this one, and we'll say, let's go for 6, what should we do, 6, 15, 20, and then some multiple now, and I'm using a lambda and mu again, you might see S and T, let's go for 2, 4, 6. So if these are to intersect, what we assume then is 7 minus 2 lambda must be equal to 6 plus 2 mu. That's telling me now that the I components of these two lines must be the same. Minus 4 plus 3 lambda must be equal to 15 plus 4 mu. Okay, so now 6, let's make sure we write these down, 6 minus lambda is equal to 20 plus 6 mu. Now often you'll see that when you write these out you make mistakes, so be very, very careful. Now let's call this equation 1, let's call this equation 2, and let's call this equation 3. What we're simply going to do now is solve for one of these. So let's say we took, let's say I take equation, let's just see if there's any easy ones to work with from here. Let's say we take equation 1 and double it up. So that's going to be 14 minus 4 lambda will be equal to 12 plus 4 mu. So that now is equation 1 just doubled up. So all I've done is times this by 2. Okay, now if we take equation 2, we've got minus 4 plus 3 lambda is equal to 15 plus now 4 mu. So all I'm doing is solving simultaneous equations for lambda and mu here. So let's go ahead and subtract these two. So 14 minus minus 4, that's 18. Then we're going to get minus 7 lambda will be equal now to, what's that going to give me? Minus, just subtracting down, that's going to be minus 3. Okay, so what's that give us? 21 is equal to 7 lambda. That's working out quite nice. Lambda is equal to 3. So if we take this to be true, and if they are going to intersect, now we can say lambda is equal to 3. So subbing it into either one of these, so 1 or 2, we can solve for mu. So let's solve for mu. So we're going to get minus 4 plus now 9 will be equal to 15 plus 4 mu. So all I've done is sub now lambda into equation 2. So what's that going to give me? That's going to give me now on here minus 4. So what we're going to have? We're going to have minus 4 plus 9, which is going to give me 5. So 5 is equal to 15 plus 4 mu. And then what's that going to give me? That's going to give me now minus 10 is equal to 4 mu. So we can see that mu is equal to minus 5 over 2. Now, if that's the case, that's where these points now, the values of lambda and mu, where these would intersect. All we need to do now is take this and show that it doesn't work in equation 3. So let's see, we got 6 minus, this remember is equation 3. We got 6 minus 3 is going to be equal to 20 and then plus 6 lots now of minus 5 over 2. So all I've done is sub this in right here. Lambda and mu are in here. So what's that going to give me? 3. And then we should have on here, what's that going to give me? 17 minus, what have we got? Sorry, minus 5. That's going to give me 5. So what's that going to give me? 3 times minus 5 is minus 15. So that's going to give me 5. So we can see, we can say, therefore, they don't intersect. So don't intersect. And we can say that these are skew. So don't intersect and are skew. And you need to show that. You assume that they're going to intersect. You go ahead and solve for lambda and mu in one of them, get these values, and then put it in here and show that they don't intersect. So hopefully my working's done okay on that, and that stacks up. But that shows us now 3 different scenarios. So our 3 different scenarios, parallel vectors, we've got the vectors that intersect, and then those that don't. So if you just want to see this now as an aeroplane going here, or even pipes in a warehouse or something, this pipe is going to sit above it. It looks like they intersect, but as stated, that distance between them could be 100 metres, it could be 10 centimetres. So there we go. That's a brief introduction, well, brief as half an hour is, on the vector equation of a line. Vector equation of a line, as seen, we can write it now as r is equal to some position vector A plus a multiple, we use lambda or mu, of a direction vector. In general, r will be equal to A plus lambda, and then we'll have A, B, where A and B are simply direction vectors. In later videos, we'll look at the angle between 2 lines, and we'll look at a range of properties with these and applications of them. But hopefully now, and I'm kind of hoping that my maths has stacked up here. If it hasn't, hopefully you'll see what you're doing with skew lines, parallel and intersecting lines, and you can go from there.